Hello and welcome. In this video, we're going to talk about properties of logarithms, how those relate to properties of exponents, and how we can use those properties to expand or condense logs that have the same base. So let's go ahead and jump right in. So we know that a log is an exponent, and because of that, some of the properties that we have learned in previous lessons that apply to exponents of the same base, similar properties should apply to logarithms of the same base. So we know that if we have b to the power of m times b to the power of n, that since these are the same base and we're multiplying them, that turns into addition. What that's going to look like with logarithms is that if we are multiplying two logs of the same base, we can separate that out to become addition. Similarly, we know that when we divide, if we have the same base, we subtract our exponents. That same thing is going to be true here. If we're dividing two log portions that have the same base, that's going to turn into subtraction. So here we're going from one log to two logs, one log to two logs. And then the one that actually gets used quite a bit is this power to power property. We know that if we have power to power, we multiply. What that looks like with logarithms is that this exponent can be multiplied after we deal with all of this, so it can sort of plop down in front. So instead of me just telling you these properties, what I actually want to do is just do a quick proof to show you that it actually makes sense for these properties to apply. But the key thing that you remember is that multiplication and addition go together, that division and subtraction go together, and that we can drop that power in the front. But let's talk about where they come from. So if I'm going to establish a relationship between exponents and logs, since a log is an exponent, I need to be able to convert back and forth between exponential form and logarithmic form. So I'm going to start by just defining m to be log base b of x and n to be log base b of y. Now let's go ahead and rewrite both of those expressions in exponential form. So if I convert this to exponential form, I'm going to get b to the power of m is equal to x, and here I'm going to get b to the power of n is equal to y. And now that we've done this, let's talk about the product rule first. So let's look at the product rule, which means let's go ahead and multiply x times y together. In this case, that means we're going to be multiplying b to the power of m times b to the power of n, which is b to the power of m plus n. Now I want to look at how these properties relate back to logarithms. We already knew how they related to exponentials, so let's go ahead and take the log base b of both sides. So what we learned in the previous lesson, this is going to stay the same, log base b of x times y. What we learned in the previous lesson is that these are inverses of each other. Log base b of b is just equal to 1. So this is going to become m plus n. And what were m and n? M was log base b of x, and n was log base b of y. So we have now proven that this property works, that multiplication can be expanded out into addition. So if you're feeling like that was really cool, I want you to see if you can prove a similar relationship with division. So we're still going to use this starting information, and now we're going to talk about the division property. So you can think about it, or the division rule, in the same way. What happens if we start with x divided by y? So again, pause the video and try and work through this on your own if you're feeling like you might be able to get there. Okay, well, this is going to be equal to b to the power of m over b to the power of n, which we know simplifies because of properties of exponents to be m minus n. Now we're going to do the same thing we did over here. We're going to take log base b of both sides. This side is going to remain the same. And on this side, this is the identity, so we are left with m minus n. And what were m and n originally? They were our log statements, right? So this is log base b of x minus log base b of y. So if you really like math and you are planning on going on to higher level classes, this is a great process to be into. Never accept something to be true, but seeing the proof of why it's true and how it works just really is going to solidify your understanding of these topics. So I'm going to erase this, but let's lastly talk about the power property and just do a quick proof of that. So we're going to start with letting m be log base b of x. And then what we're trying to do here is we're trying to raise both sides of the equation to a power. But also let's convert this. So this is b to the power of m is equal to x. Now let's go ahead and raise both sides of the equation to some power, because that's what we're trying to figure out is what happens if I raise both sides to some arbitrary power. So let's raise both sides to the power of k. So we know that this is just going to be b to the mk equals x to the power of k. Again, we want to see how this ties to logarithms, so let's go ahead and take log base b of both sides. We can again use this identity that this is 1, so we're left with mk over here. But what was m originally defined to be? M is log base b of x. And what is happening with k? K is being multiplied there. So that gives us this statement. And what this statement really means is that we can drop this exponent in front, deal with the logarithm, and then multiply by that exponent afterwards. So now that we've seen the proofs of these, let's go ahead and talk about how they work and how they can help us and look at some examples where we're going to be using them to approximate logarithm values and to expand and condense. So now that we know these properties, and let's just kind of summarize them, that when we're multiplying, this can be split with addition or vice versa. Let's make those arrows go both ways. When we're dividing, this can be split with subtraction. When we have a power, it can be moved in the front. Those basic properties are going to help us both expand and condense expressions that have logs of the same base. So something really important here is that these properties only apply when we have logs that have the same base value. Why is it helpful to be able to expand and condense? Well, it gets used in higher level classes like calculus to take something that's really complicated if it's looked at as a product. And if we split it into a sum, it actually becomes something easier to work with. In classes like this one, it gives us the ability to condense something down into something smaller, which actually might be easier to solve or analyze what's happening. So let's talk about expanding first. If we're expanding, our goal is to take one log and expand it out into many using those different properties. So you're going to ask yourself, what is each piece doing? So 5 and x and y, what are they doing? They're all multiplying. What operation does that lead me to? Multiplication is going to lead me to addition. So make sure each piece that you're doing this, when you're expanding, each piece is going to get a log with an appropriate base. Make sure that you're correctly using the property. And when you think you're done, ask yourself this question: is there more that can be expanded? So looking at log base 3 of 5x squared y, I know that the 5, the x squared, and the y are all being multiplied. And there's 3 different things that are being multiplied: 5, x squared, and y. That multiplication can be expanded using addition. So log base 3 of 5 plus log base 3 of x squared plus log base 3 of y. We're splitting each piece into its own log-based entity. So now I'm going to ask myself if I'm done. Well, log base 3 of 5, there's nothing to split here. There's no division, there's no multiplication, there's no exponents. So I'm done with this piece. Log base 3 of x squared, oh, I have this squared sign. How can I simplify this? This squared sign, based on the power property, can actually move in front here to make this 2 log base 3 of x. So I'm going to go ahead and keep this first log the same. And now I'm going to move that 2 to the front. 2 times log base 3 of x. Plus, and then I'm going to ask myself, is there anything that can be simplified here? Y can't be simplified anymore. Log base 3 of y can't be simplified anymore. So I'm just going to rewrite log base 3 of y. So before we move on to condensing and work through example B, let's go ahead and work on 1, 2, and 3 below, all of which we are expanding. So we're taking one log and we're splitting it into multiple logs. So each time I really want you to be asking yourself what is happening between the different terms. So I'm going to go ahead and look at number 1 here, and I notice this 5x to the 7th. So I'm asking myself what operations are happening here. Well, 5 and x to the 7th are being multiplied, and y is being divided. And then I also have this exponent that I'm going to have to deal with. But let's deal with this one piece at a time. Let's deal with the division first. Natural log of 5x to the 7th. If I'm going to get rid of this division is going to go to subtraction. So minus natural log of y. So now I've gotten rid of the denominator. Notice I went from 1 natural log to 2 natural logs. This one over here can't be simplified anymore. So now I'm going to look back here. Natural log of 5x to the 7th. So I have a product happening here. A product can be split. Multiplication is going to go to addition. So natural log of 5 plus natural log of x to the 7th minus natural log of y. And lastly, I can deal with this exponent. That's going to go in front of the natural log of x. Notice it's not going in front of the whole thing because this 5 doesn't have an exponent other than 1. It's just natural log of 5. So natural log of 5 plus 7 natural log of x minus natural log of y is going to be my expanded logarithmic expression. And I'm double checking each term. There's nothing more I can do so that I know I'm done. So I'm going to encourage you to pause the video and try and work through numbers 2 and 3 on your own. Looking back at the 2 examples we've done together, making sure your answer, each piece, each term that's being separated by a plus or a minus sign, each of those terms has its own separate log. So hopefully you've had time to work through this. This here is multiplication. That multiplication is going to go to addition. So log base 6 of 3 plus log base 6 of x to the 4th. Nothing more to simplify here, but here we have an exponent that can plop down in front. So this is going to become 4 times log base 6 of x, and I still have log base 6 of 3 plus that in front. Multiplication can expand using addition. For number 3, I'm going to deal with the division first. Natural log of 5 minus natural log of 12x. What I want you to see is that I'm actually putting parentheses around that 12x because that's a multi-part term. Now, it doesn't mean anything different if there's not parentheses here, but what I want you to see is that there is a product happening here. That product can be split into 2 separate pieces. So natural log of 5 minus, if I expand this, this is going to be natural log of 12 plus natural log of x. But remember, both the 12 and the x were in the denominator. So this negative sign is going to actually need to distribute to both the natural log of 12 and the natural log of x. So our goal is always going to be to expand completely. If you don't distribute that negative, you haven't completely expanded every part out. So now that we've talked a little bit about breaking things up into smaller pieces, let's talk about putting them back together, or condensing, consolidating, putting them down into one term. So our ultimate goal when we're condensing is to be able to simplify it down to have one log of that same base. So let's clear some room and look at example B. All right, condensing. Same basic idea. Make sure that we're doing the opposite of what we were doing before. We are trying to get down to just one log, and make sure that you're only doing that with things that have the same base. Make sure you're applying the property correctly. Now we're going to go from subtraction to division, from addition to multiplication, and then always ask yourself, is there more that I can condense? Is there a term in front that can be moved to be an exponent? We want to condense as much as we possibly can. So I like to work left to right here. Let's talk about what's going on here. Log base 2 of 9 minus 4 times log base 2 of x. So actually the very first thing that I'm going to do is I'm going to leave that subtraction, but I'm going to move the 4. That 4 in front is going to become an exponent here. Now I'm going to deal with the subtraction. Subtraction is going to go to division. So log base 2 of 9 divided by x, and then I'm going to keep this blue, plus log base 2 of y. And now I'm going to simplify this addition. Addition goes to multiplication. So I'm going to multiply that y. So this is going to become log base 2 of 9 times y divided by x. And I like to put parentheses around it so it's clear that that is what we are taking log base 2 of. This is much more concise than working with something like this. Let's do a few more examples with condensing. Okay, for number 4, just as a reminder, there is no base written. Ask yourself, what does that mean the base is? Well, that's a common log. It means it's base 10. Doesn't mean you have to write the base 10. It just means that it is, in fact, base 10. So let's deal with exponents first. So this is going to still be log of 9 plus log of 2, but 2 to the power of 3, minus log of 3. And I'm actually going to simplify that one more. 2 to the power of 3 is 8. So let's just go ahead and simplify that to be 8. Now, log of 9 plus log of 8, that addition can simplify to be multiplication. And what is 9 times 8? It's 72. And that subtraction can simplify to be division. So that's going to be 72 divided by 3, log base 10 of 72 divided by 3, or log of 72 over 3. And since we don't have any variables here, we just have numbers, we can simplify those numbers. 72 divided by 3 is 24. So this is log base 10 of 24. So we took this very complicated looking sum and difference here, and we condensed it down to be one single logarithm, which we could actually evaluate on a calculator. I'm going to encourage you to pause the video and work through 5 and 6 on your own. And I know that natural logs, they look different, but everything is going to apply in the same exact way. So go ahead, pause the video, work through them, and then unpause the video and see how you did. So on number 5, there's just one thing to condense, the x and the 9, and we're subtracting, so that's going to condense with division. On number 6, we can move that exponent first. 3 to the third is going to be 27. Then the natural log of 4 and the natural log of 27, that can become multiplication. So 4 times 27 over the 12, since we are also subtracting. And you could do that in 2 steps as well. Natural log of 4 times 27 minus natural log of 12, and then you could condense further. Now, instead of multiplying 4 times 27 and then dividing by 12, I'm going to go ahead and simplify here. 4 over 12 is 1/3. 27 divided by 3 is 9. So this whole messy looking logarithm actually simplifies just to be natural log of 9. So now that we've talked about expanding and condensing, let's put those skills to the test and see if we can apply them in a different style problem. So if we have some information about different logarithms, like you'll see here, and we're being asked for something different, we can use the properties of logs we just talked about to help us get there. So if we're given information about log base 2 of 3 and log base 2 of 7, since we know how multiplication relates to addition, how division relates to subtraction, and how powers work with logarithms, we can use those tools to try and help us approximate a log without actually having a calculator. So some tips that I have for you here. Think about what's being given. So in this case, log base 2 of 3, log base 2 of 7. What's being given and what information you have and how you might be able to rewrite that number using those two numbers. So when I look at 9, log base 2 of 9, I know that 9 is 3 squared. So my first thought here is, okay, could I do something with the fact that 9 is 3 squared? Well, that means this logarithm is the same thing as log base 2 of 3 squared. And what are we allowed to do with this 2? We're allowed to plop it in front. And why is this helpful? This is helpful because we know that log base 2 of 3 is approximately 1.585. So this is approximately 1.585. What that means is I can go back to what I was originally being asked, log base 2 of 9. This is going to be approximately 2 times 1.585, which we could do by hand to get 3.170. So we were approximating log base 2 of 9 using log base 2 of 3 and knowing that we could use this property to move the 2 in front. So here on example 7, we're looking at log base 2 of 3 divided by 7. Well, we know what log base 2 of 3 is, and we know what log base 2 of 7 is, and we know that this could be expanded using subtraction. What that means is log base 2 of 3 over 7 is going to be approximately, well, what's log base 3 of 2? 1.585. And log base 2 of 7, so minus 2.807. And then we can perform that subtraction to get that log base 2 of 3 over 7 is approximately negative 1.224. So I'm going to encourage you to pause the video and work through numbers 8 and 9 on your own. How can you rewrite 21 as something involving multiplication, division, or exponents with 3 and 7? Same thing with number 9. How can you rewrite log base 2 of 49? Or how can you rewrite 49 using multiplication, division, or products of 3 and 7? Then unpause the video and see how you did. So on 8, 3 times 7 is 21. We can expand that with addition, which means we can then say that log base 2 of 21 is approximately 1.585 plus 2.809, which means log base 2 of 21 is approximately 4.394. So 49 is 7 squared. I can drop that 2 in front of our logarithm. So log base 2 of 49 is the equivalent to 2 times log base 2 of 7. What that means is that log base 2 of 49 is approximately 2 times 2.809, which means that log base 2 of 49 is approximately 5.618. So what we just did was we approximated these values, but if you look at the original problem on any of these, log base 2 of 49, there should be a way to just input this on the calculator to find the exact value. But as we talked about in a previous lesson, your calculator is in common log base, so anytime you type something in, it is in log base 10. So how do we do this on our calculator? How can we manipulate this so instead of getting an approximation, we can find the exact value? The answer to that question is that we can use the change of base formula. So logarithms with any base other than 10 or e can be rewritten using log base 10 or using log base e if we had natural log. This allows us to evaluate any logarithm on a calculator. So the way that this works is if we have log base c of a, we can rewrite that as log of any base, which we're going to typically be choosing 10 because that's what our calculator naturally does, of a over log base, again, that number we're choosing, of c. The easy way to remember which goes where is that the base goes in the basement. So that base number goes in the bottom part of the fraction. So what does that mean? That means if you have something like log base 2 of 17, you could evaluate that on your calculator by doing log of 17 divided by log of 2. And here we do have 2 logs because our calculator is going to do this in base 10. You could also do this with natural logs. If you can choose whatever base you want, you could also choose e and you could use the natural log button on your calculator in the same way that you're using the common log button on your calculator. So let's look at some examples. Grab a scientific calculator if you have one so I can show you how to do it. Okay, so first we're going to practice just rewriting these logs so that we could use our calculator. Then we'll talk about actually plugging them into the calculator. So log base 3 of 8 is equivalent to log of 8 over log of 3. Now these are both base 10 because that allows us to use a calculator. You'll notice that numbers 10 and 13 are the same. This is also equal to natural log of 8 over natural log of 3. You can do that either way. So now let's grab the calculator and let's actually see what happens when we are doing that. So if I hit log of 8, and then I'm going to divide that by, divided by log of 3, that's going to give me 1.89279. So let's just call that 1.893. And actually, I'm going to still keep this as an approximately symbol, 1.893. Let's see what happens if we do the exact same thing with natural log. So let's clear this. And now we can type natural log of 8 divided by, oops, I want to make sure my parentheses are right here. Natural log of 8, close parentheses, divided by natural log of 3 equals, and if you look, we're going to get the exact same value. So this is going to be approximately 1.893. So whether you prefer the common log button or the natural log button, they're both going to give you the exact same thing. Because I want you to be comfortable with both the common log and the natural log, what I'm going to have you do is rewrite the 4 remaining problems using the change of base formula and then practice on your calculator. And then unpause the video and see how you did. So hopefully you had time to do that. Here's the setup for the change of base, and then I'm going to go ahead and fill in the decimals on the calculator. So hopefully you had time to practice on your calculator with each of those things. But let's recap what we learned in this lesson. We proved the 3 main properties that you're going to use to expand and condense logarithms. We proved the relationship between multiplication and addition when we're expanding and condensing, between subtraction and division, and the power rule. We then used those properties to expand and condense logarithms that had the same base. We extended that a little further to look at what if we were given specific information, how can we manipulate that log to use that information to come up with an approximation, and then how can we use the change of base formula to enable us to actually evaluate any logarithm using our calculator, whether we prefer to use the common log or natural log. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.